Welcome everyone, I'm J Wildberger, and this is our series on elementary mathematics explained. Today we're going to be looking more at measurement, and at measurement on a finer or smaller scale, where there's lots of practical things, actual activities that children can be encouraged to do to solidify their understanding of abstract sort of arithmetic, connecting it with the real world, manipulating objects and measuring them. So we're talking about weighing in grams and ounces now. Now I remind you that there's basically two weighing systems in the world today where we're measuring how heavy something is. Okay? So the weight of an object is ultimately due to the force of gravity, which is the force between the big planet Earth and the object that we're talking about. Any two objects attract each other, and this is resulting in the force of gravity down, and it's really the measurement of that force that is exerted on an object, which is its weight. Subtly a little bit different from mass, which is a little bit more of an advanced concept. Okay, so there's two methods or two systems for measuring weight. The metric system with kilogram as the essential main unit, and then some smaller units, the gram, and maybe also a milligram, and a bigger unit, a metric ton, or ton with double N-E. And the relationship between these various units is all in terms of factors of 1,000. So 1,000 is a pretty big number, but that's very important in this system. So 1,000 grams is a kilogram. 1,000 kilograms is a metric ton. And if we want to subdivide a gram into something even much smaller, we have a milligram. 1,000 milligrams is equal to a gram. In today's lecture, we're going to be talking mostly about the gram. We've been talking about already the kilogram side of things, where we're talking about objects which are, roughly the same weight as people. With grams, we're talking about smaller quantities, measuring often weights of things associated with cooking, okay, or just small household objects. Now, in the imperial system used in America and a few other countries in the world, we have ounces, pounds, and tons. So the pound is the standard unit. It's about a half a kilogram, or in other words, a kilogram is a little bit more than 2 pounds. Now, in the imperial system, it's a little bit different. We're having a subunit of ounces, and there's 16 ounces to a pound. Okay, so the number 16 figures prominently in this system. And to go from a pound to an imperial ton, you have to multiply by 2,000. So 2,000 pounds is a ton. Because a kilogram is roughly 2 pounds, that means that a metric ton and an imperial ton are more or less the same, just a little bit bigger, the metric ton. Now, this system here is by far the most important because it's what's used in the scientific world. So in science, we almost universally use this system. And in fact, the units themselves are calibrated much more carefully in this system. Right? There's a lot of international focus, especially on defining the kilogram. And the imperial system these days is pegged to the SI, or the metric system. So for example, the actual definition of a pound, or maybe say an ounce, that 1 avoirdupois ounce is 28.349523125 grams. Now, avoirdupois refers to the fact that there's actually two systems of pounds and ounces. This is the more familiar one that's used for everyday objects, but also there's a related but slightly different system that's used for metals, like especially precious metals like gold and silver. So we're not going to talk too much about that, but okay, you just be aware that the imperial system is a little bit more complicated. And notice the huge amount of accuracy here in terms of pinning this ounce to the gram. Okay, so in today's lecture, we're going to be looking at measuring in this realm, where we're looking at things in terms of how many grams they weigh, or in terms of the number of ounces that they weigh. But we'll be concentrating mostly on the metrical system, because that's the most important throughout the world today. So let's start by getting a sense of the size of a gram. A gram is actually a very small unit of weight. And for example, it's roughly the weight of a paper clip, a standard little paper clip. That's a gram. A US dollar bill also weighs a gram. And a small thumbtack might weigh a gram. So that gives you a rough idea. So it's a very, very small unit. How about a few bigger things? Well, a sheet of paper, like this, A4 paper in Australia, maybe 8.5 by 11 in America. This will weigh around 5 grams. Okay, 5 grams. And notice that we abbreviate gram with a simple G. Okay, so 5G means 5 grams. A AAA battery, like this one here, all right, that's a AAA battery, that weighs around 12 grams. A tablespoon, something like this, that would weigh around 50 grams. A small jar of Vegemite, what people eat sometimes in Australia, Vegemite. B vitamins for vitality, it says. Okay, so this thing here is, well, it says 235 grams, but actually, if you actually weighed the whole thing, it'd be more like 350 grams. Okay. Now, with young children, it's great to get them involved in some physical activity that will reinforce their understandings. And this is a great place to do that because we can go now around the house or around the kitchen and weigh various objects. Now, in order to do that, we need some kind of scale. And, well, there's different kinds of scales. Here is one kind of scale. It's just a kitchen scale where you place an object on top and you read off weight down here. So that's a kitchen scale. Another kind of scale that you sometimes see is one that has a sort of spring in it more directly. So there's a stand there and a little tray up on top, which is compressed when you put something down, and then there's a needle that will physically read off the weight of whatever you put on top. Now, this is not so different from a ruler in some sense, because when we measure something with a ruler, it's also very physical. But there is an interesting visual difference here in that just looking at objects is not enough when measuring weights. Okay? When measuring lengths, you have some object, you can just look at it and see what the length is. That's not the case with weights. The size of an object, physical size, is an indicator of the weight, but it's not all that you need to know. So here's an example of that. I have two cans from the kitchen. So here we have a can of tomatoes, certified organic tomatoes. And over here we have a can of Cadbury drinking chocolate. Okay, so they are roughly about the same size, same height. And if you put one on top of each other, they're the same width. So physically they're the same size, but they're actually quite different weights. In fact, on here you can read this as 400 grams, this one, and this one says 225 grams. Okay? So there's an aspect of density here, which is really an ingredient, which we'll talk about at some further point. But kids should just be aware that there's something different about the tomatoes and the drinking chocolate that results in them having different weights, even though the sizes are the same. Okay? So it's a little bit, it's not just size, it's actually weight that's important here. So if you're a teacher of young people at elementary school, you definitely want to have certain implements in your classroom that allow students to directly access some of these concepts. For example, kitchen scales. Very important to have some kitchen scales in your classroom. And another thing that's very useful is an even more ancient technology, much simpler kind of thing, which is a pan balance. Where we have some kind of system like this, where ultimately there's sort of a lever that can rotate around some point there, and with weights, pans attached on either side, so that we can then determine whether two objects have the same weight or not, or more generally, which of two is heavier or lighter. Okay, so this is an ancient technology that compares weights. It's not so much telling you what the weight is directly, because there's no place where you can read off something, but it's a way of measuring the relative weights of two different things. So for example, here I have a banana in this pan, and we put an apple in this pan. And suppose that after we do that, the apple goes down and the banana goes up. What does that mean? It means that the apple is heavier than the banana. Okay? Because the apple is going down, it's pushing down further. So this then relates to some fundamental inequalities in mathematics. These are very important relations. Of course, there's the equal sign, but there's also these other two symbols standing for less than and greater than. Okay? So when we say apple less than banana, that would be the case when the apple weighs less than the banana. Or in other words, the banana is heavier. If apple equals banana, then we would expect that the balance would be equal. They would be on the same level. It wouldn't be teetering one way or the other. That's equality. And if apple is bigger than banana, well, that's what's happening here. The apple would go down. So in this particular case, with this configuration, we'd say this is the possibility that's relevant, that explains the relationship between the apple and the banana. Okay, strictly speaking, between the weight of the apple and the weight of the banana. Okay, so we have an introduction here, a physical introduction of these three important relations: less than, equal, and greater than, in the context of a pan balance, something very direct that students can experience. Now, if we wanted to weigh something with a pan balance, we could do that, but we would require some additional tools. We would require some standardized weights. And this is a great thing to have also in a classroom. Okay? There should be a set of standardized weights around. And how does that work? Well, what we have is we have typically metallic objects which have been pre-configured to have exactly a certain amount of weight. So you might have a metallic block there weighing, say, 1 kilogram. And then a smaller one weighing 500 grams. That's half of a kilogram. Or in other words, 1 kilogram is 2 of these, because 500 plus 500 is 1,000, and 1,000 grams is the same as 1 kilogram. Okay? So this is the biggest weight in our collection, and then this is the next one. And then we might have, for example, a 200 gram weight, and then a 100 gram weight. And these would also have their markings on top of them, so you could just read off what they are. But 100 grams is still reasonably heavy, so we might have some smaller ones. They might have some different shape, maybe some small discs, 50 grams perhaps, 20 grams, 10 grams, 5 grams. You could even have a 1 gram weight. Okay? So if you have enough of these around, then what you do in order to weigh something is the following. So you take your pan balance. Let's say you want to weigh that piece of broccoli. Okay, so you put the broccoli in one pan. Of course, when you do that, that immediately goes down, that immediately goes up. So the idea then is to take some collection of weights and put them in the opposite pan to make things equal. Okay, so you might, for example, try 500 grams. You put 500 grams in there and see what happens. Well, if the 500 grams is too much, it'll go down. The weight will be here, the broccoli will be up there. Then that means that's too much. So we would take that out and substitute a smaller weight, maybe 200 grams. So if we put a 200 gram in there, then perhaps the broccoli would go down and the weight would go up. That means that we are going in the right direction, but we need to put more stuff in here. So we might have to put 2 of these in, and maybe 1 of these, and maybe 2 of those, and maybe 1 of those all together. And then we would get a situation where at some point we're balancing or pretty close to balancing. And then the idea is that we can then read the weight of the broccoli by summing up the weights of all these standardized weights that we've put in the opposite pan. Right? So the pan balance can be used to weigh things. And for thousands of years, this is the way people did weigh things. Okay, they didn't have scales, at least not in most primitive cultures, they would have had some kind of balance and some standardized weights exactly in this direction. So this is a great thing to have in your classroom also, to have some sets of these so that students can, first of all, weigh things using a balance, but they also get a tangible physical understanding of the difference between a 10-gram weight and a 100-gram weight or a 500-gram weight, because they can see and feel these objects. They're concrete and they're tangible. Okay, so that's what we want to do. We want to connect their theoretical understanding of pure numbers with something that's practical and tactile. All right, so now we can suggest this alternate activity, which is also measuring household objects or kitchen objects, but by using a pan balance and some standardized weights. Okay, so it's a little bit more work than just putting something on a scale and reading off the weight. Now we have to do some more work. We have to adjust things. We have to, now it's heavier, now it's lower. We have to sort of have a more direct experience with the numbers and combining them. So it's very useful. So for example, if these are the weights that we say had to put in the pan to balance something else, maybe a piece of broccoli, we see there's a 500, a 200, maybe a 50 and a 5, then we would deduce that the weight of whatever it is would be 500 plus 200 plus 50 plus 5. This is addition. These things are being added. And hopefully we'll be able to figure out that this is 755. So we also get to practice some addition. Great. So this gives kids a direct tactile experience of numbers in the range 0 to 1,000, because that's where we go from 0 to a kilogram. In the gram scale, we're going from 0 to 1,000. So it's quite a wide range of numbers, and we're getting experience with the relative magnitudes and the arithmetic of numbers in this range. That's very important. All right, so we're touching base with the counting numbers here. When we're measuring in grams, because gram is such a small unit, typically we're always using whole numbers of grams, unless we're making some really, really fine calculation, maybe in some kind of chemical experiment or something. So typically you never have to go to fractions of a gram when you're dealing with ordinary, everyday kitchen objects. Okay, so we're looking at the scale from 0 to 1,000, and prominent amongst that range of numbers are the numbers 0, 100, 200, 300, 400, 500, 600, 700, 800, 900, and 1,000. So they're kind of the equivalents, the stepping stones by 100. It's like counting from 0 to 10, but now we're multiplying everything by 100, counting from 0 to 1,000 by hundreds. Okay, and having some sense of the relative positions in this system of numbers from 1 to 1,000 is very useful thing. So even though we do use a decimal system of numbers based on base 10, nevertheless, even in this decimal system, thousands play something of a distinguished role. Okay? And we can see that when we represent numbers in the usual fashion. So something like this, 753, 411, 126. The way we would read this, well, first of all, the way to understand it is maybe to start from the right-hand side. So here's 126. And then this next group of 3, which is 411, it's like 411. That represents the number of thousands. Okay? So if we just had this here, it would be 411,000 and 126. So we read it in groups of 3. If we add a further group of 3, 753, that would be 753, and we would read this as millions. So 753,411,126. So the commas are separating thousands here. So we have thousands, and then millions. Then if we had another triple, that would be billions, and then a further triple would be trillions. And so 1,000 times 1,000 is a million, and 1,000 times a million is a billion, and 1,000 times a billion is a trillion. And I'm aware that different places in the world, this system is not always used this way. Sometimes in Europe, the meanings are somewhat different, but this is what we're going to stick to, okay? So 1,000 thousands is a million, 1,000 millions is a billion, 1,000 billions is a trillion. So it's 1,000 that leaps us from one big unit system to the next bigger unit system. Okay, so it's another reason why understanding and having an appreciation for 1,000 is important. That going from a gram to a kilogram is repeated in a lot of other contexts, both in measurement and just dealing with numbers generally. So after children have some sense of the three relations, less than, equal, or greater than, corresponding to using a pan balance and figuring out which of two objects is heavier and which is lighter, then we can move up to thinking about ordering weights or ordering objects by their weight. So for example, maybe here are three things from the fridge. There's a banana, an apple, and a piece of broccoli. And we might be interested in which of these is heaviest and which is lightest. So now we have three things, and what we want to do is not compare two of them, but we want to put them in order. Okay? So we're arranging objects in order of weight. That's what we're thinking about here. Now that order of weight could be increasing order. So we want to start with the lightest one, and then a little bit heavier, and then a little bit heavier until finally we get to the heaviest one. But maybe in some other context, we would want to have them arranged in order of decreasing weight, with the first one being the heaviest and the last one being the lightest. Okay? But in either case, we want to establish this idea that we're ordering things. We have the sense of greater than and less than. That means if we have a number of things, we can put them in the right order. Okay, so a pan balance, of course, can be used for this, but it's probably fun for kids just to use their hands because you have two objects, you want to figure out which is heavier, well, you can use a pan balance, but if they're not too close, you can just sort of use your hands like this and figure out that this one's heavier. You can feel that. It's direct, it's tactile, it's powerful, okay? So you can have, half a dozen different objects, and you can just ask kids to arrange them in order just by weighing them with their hands even. Okay? Tomato, or apple, I guess. Broccoli, which one is heavier? And then arranging the fruit in order of weight. Now, a lot of what I've been talking about applies also to the imperial system, where we have ounces and pounds instead of grams and kilograms. And there the relation is that 16 ounces is 1 pound. That's quite a different system from 1,000 grams equaling 1 kilogram. For sure, 1,000 grams is harder to deal with. It's a little bit more complicated, but it is at least a power of 10, so there's an advantage there. But with the ounces and pounds system, it's somehow a little bit maybe more elementary to appreciate how much an ounce is because it's not such a very light unit. So an ounce is roughly, say, a slice of bread. That would be 1 ounce roughly. An iPhone, maybe around 6 ounces. An apple, maybe around 5 ounces. And so the similar kinds of things that I've suggested for the metrical system can be done here in the imperial system. You can get students weighing things, you can get students balancing, you can get students ordering objects. But here then the emphasis is on the 16. We get a bit more intuition and understanding of the number 16, which is actually quite an important number because it's a power of 2. It's 2 times 2 times 2 times 2. And we can see that sort of here physically. If you have 16 objects, then you can divide them into 2 equal groups of 8. 8 there and 8 there. So 16 is 8 plus 8. And if you take 8 objects, well, you can divide them equally into 2 groups of 4. So 8 is equal to 4 plus 4. And 4, similarly, can be divided into 2 plus 2. And of course, 2 can be divided into 1 plus 1. So there's a nice sort of binary subdivision associated with 16 because it's a power of 2. And so learning about ounces and learning about weights with ounces somehow leads one to more experience dealing with these powers of 2. Because half a pound will be 8 ounces, and half of that would be 4 ounces. Though we haven't actually talked about halves yet, but okay. All right, so there's some advantages in both systems, but whatever system you're using, this is a great place to connect abstract arithmetic with real-life measurement, almost sort of a bit of science, and get students to get a physical intuition and familiarity with our number system and its usages. In our next video, I want to talk about a closely related concept of volume or capacity, which is very closely connected with measuring weights, but is subtly different and also very important around the house. And once we have those two things together, then we'll be able to try our hand at some cooking and see how mathematics can help us in the kitchen. Hope you'll join me for that. I'm J Wildberger. Thanks for listening.